Welcome to class. We've got a lot to go through today, so we're going to go ahead and get started. So welcome, everybody. I've had a few people who tried to submit the Stats Matter activity from last week, and there are some people who couldn't get it uploaded. I've changed one of the settings, so that should allow you to upload it. It's only available until the end of tonight, so if you're planning on uploading, do make sure you get that in today, please. Okay, so let's go ahead and begin. All right. So today, guys, we are going to talk about correlations and briefly about some of the things that you should be thinking about that might affect a correlation relationship. But the main part of what we're going to talk about is how correlations then lead into this idea of linear regression. And linear regression is a really important topic. In fact, it's going to form the basis for what we talk about basically for the rest of the semester. So do make sure that you have skimmed through your textbook. If you have any questions at the end of today, please make sure that you go back to your textbook. Everything I discussed from today is in your textbook. That is intentional, so you guys have that resource always available to you. There's a lot that we're going to go through, and I'll keep coming back to these concepts throughout the rest of the semester because when we talk about the ANOVA is based on the general linear model, which is the basis for linear regression. So we'll come back to these topics over and over, so they should hopefully become very familiar to you. But do make sure that you remember that your textbook has this information. So if at the end of today you're like, oh my gosh, that was a lot, because it will be a lot today. I'm forewarning you guys right now. You do have a resource available to you at all times. Of course, you also have the discussion forum, and I've had a lot of great questions. The tutors and I have been very busy responding to your questions, so keep those up. You guys have been great about using that. Okay, so here's what we're going to discuss for today. We'll talk about correlations. We'll talk about linear regression. We'll start off very simple with hence a simple linear regression with one predictor, and then we'll talk about how this can be extended into a multiple linear regression with multiple predictors. So to start us off, I have a prompt. This comes from a podcast I was listening to recently from the Harvard Business Review, and it said that they're just talking about a study that this person recently did, looking at how people spend their free time and how this is related to life satisfaction. And this person said, people who find more joy in their free time have greater life satisfaction. It's not how much time you have, it's not how much free time you have, but it's how much joy you're able to get from that free time. And so then they talk about ways in which you should be able to improve your overall life satisfaction by finding more joy. So they go through some different tips for how you can find more joy as a way of improving your overall life satisfaction. So I want you guys to go on to the Woo Clap and just think, is there anything wrong with this? Is this thing okay, or do you have some perhaps critiques about this? Okay, so as you guys are putting in your answers, let's go ahead and start looking at them. Okay, so what do we see? At the very top, we see that correlation does not equal causation, and that's really one of the big things I want you guys to think about, is that, even though there is a correlation between the finding joy in your free time, this doesn't mean that finding joy causes you to have a higher life satisfaction. It's not necessarily a direct correlation or a direct causal relationship. So if you find other ways to increase your joy, that's not necessarily going to mean you're going to have greater life satisfaction if these two variables are in fact not causally related to each other. Good. What else? Maybe a third variable. Absolutely. So there could be something else that is producing this correlation. Hence, increasing joy is not necessarily going to increase your overall life satisfaction. States causation when no experimental manipulation was made. Absolutely. So again, this is a correlational design. We can't know for certain that increasing joy in your free time is going to necessarily increase your life satisfaction. So very good. So lots of responses here about how when you do this kind of design, we are doing a correlational design, and we cannot make these kinds of causal conclusions. And I mean, this is coming from the Harvard Business Review, right? So this is something that is pretty high, prestigious, and yet they're still making this kind of mistake of trying to draw causal conclusions from a correlational study. So I want you guys just to be aware that these kinds of errors occur a lot, and you need to be vigilant and on the lookout, because if it's coming from Harvard Business Review, you know it's coming from many other places as well. You tend to see these kinds of assumptions being made about people don't necessarily say, finding joy causes increases in life satisfaction, but they're implying it by saying, but if you increase your joy in these areas, we expect to see increases in life satisfaction. And that's basically saying they expect a causal relationship, which is not something that they can support based on the design and based on the data that they have. All right, great job, guys. So let's move on. So this is going to lead us into our discussion about variables that can influence correlations and why we need to be mindful about the kinds of conclusions we can reach from correlations. So there's three things I want to cover in terms of what can influence a correlation. The first is the extreme observations. And I'm literally just referring to outliers in this case. Outliers are those data points that are unlike the others, right? And there are many reasons you might have an outlier. Maybe someone just wasn't paying attention, right? When you're doing your experiment or your survey, somebody is just kind of like not paying attention and just responding at random. And so, of course, their responses are going to look different from the majority of people who are hopefully actually paying attention to your study. It could be that somebody truly is an outlier in how they feel, right? There's a low probability, but not an impossibility of that occurring, right? Somebody might have an extreme view on something or have an extreme behavior, right? Just recently, I just for normal health checkups, and we're getting our data heart rates checked, and mine is a normal like 58 beats per minute, and my boyfriend's is 48 beats per minute. I'm like, oh, that's really extreme. So you have sometimes where people just have really extreme like behaviors, and that's normal for them, but they're not like the rest of the population, right? So sometimes we have these extremes, and you need to ask yourself, is this something that I want in my study? Maybe you have a good reason to get rid of them. You say, I want to only study people who are within the 95 percentile of what is considered normal, or 95% within the mean. So you want to get rid of people who are maybe more than 2 standard deviations outside the mean because you want to study people who are the majority of the population, in which case maybe it's okay to get rid of the people who are on the ends of your distribution. You have good justification if that is an inclusion criteria that you have set at the beginning. But maybe you want to keep them in as well because they do represent real behavior. If you can verify that these are not people who were just like not paying attention and looking at their phones while you were doing your experiment, and that's why they have outlier data, but in fact it's a real data point, they really have extreme behaviors, then maybe you want to keep them in because that represents real behavior. It depends on what your goal is of doing research, but just note that outliers can result in a skewed or a perhaps unrepresentative relationship because they pull the correlation away from the central tendency, right? So outliers are going to make the relationship between your IV and your DV, or between your predictor and your criterion variable, maybe look a bit different from how the majority of people behave. And this is especially true when you have a small sample, right? If you have a small sample, then an outlier can cause can really have a big effect. And you guys know that when you have a small sample, you really shouldn't be trusting it that much, right? So yeah, you have 5 stars, but if there's only like 3 or 5 or 10 reviews, I wouldn't trust it, right? Go for the one that has like hundreds or thousands of reviews that maybe has a lower star rating, but that star rating is not being influenced by 1 or 2 outliers, people who are paid to give a really high review, or people who just had an unusually bad experience and tanked the review. So just keep in mind that outliers tend to have a disproportionate effect on the correlation, and that this effect becomes greater the smaller the sample size is. They have a bigger effect then. So be aware of outliers. That's why we always look for outliers when we're doing statistics, just to make sure that there's not 1 or 2 individuals who are really, really far from everybody else and kind of pulling our correlation away from what it really is. Okay, so outliers are one thing that can influence the strength of a correlation. Another thing that can influence a correlation is the fact that maybe there is a causal relationship. Sure, maybe finding joy in your free time truly is causally related to your life satisfaction. People who have more joy in their life really do therefore have higher life satisfaction, because finding joy causes you to have higher life satisfaction. So maybe we have some kind of causal relationship. But again, you guys have rightly pointed out, correlation does not equal causation. And there could be a causal relationship, but maybe you have the wrong direction. So maybe, yes, finding joy and general life satisfaction are causally related, but you've got it flipped. Maybe if you have an overall higher life satisfaction, this causes you to be able to find joy in your free time, right? It's hard to know which one comes first because it's a correlational study. It's done at one point in time, so you can't establish temporality. You can't establish precedence that changes in one variable are related to a later change in the other variable. So you don't know which variable is changing first. So it's always a possibility when you have correlations, especially if you don't have a lot of other information to fall back on, that a causal relationship exists, but perhaps in the other direction from what you originally hypothesized. Causal relationships can be influenced by third variables. A lot of you guys talked about this idea of a confound, and absolutely. Third variables are anything, I think of them as like being a ghost variable. These are variables that are unseen. In other words, they're not included in your design. So they have not been factored into your design, but they're still influencing the association. They're still influencing the result. So just because we haven't included it in our design doesn't mean that the influence has gone away. No. These third variables, they still will act in unseen ways. We're just not observing that third variable, but we are observing the effects of the third variable. So what kinds of third variables might exist? As you guys said, we have confounds, we also have mediators. A mediator is a third variable that bridges the gap between your predictor and your criterion variable. It's part of the causal chain. So maybe we have what looks to be a correlation between our predictor and our criterion variable. Fine. But in fact, the mediator is what is causing there to be a correlation between these two variables. What we see is that the changes in our predictor are causing a change in the mediator, and it's the change in the mediator that's causing a change in our criterion variable. So a mediator is part of that causal chain of events. It's the intermediary variable. So if we are looking at joy and life satisfaction, maybe there is a correlation between these. Maybe they are causally related, or maybe your ability to find joy in your free time has led you to have perhaps lower blood pressure, or you lose weight, or whatever, some kind of change in physical health, which allows you to therefore have an improved life satisfaction. And so we have a relationship between joy and a third variable, and it's the change in the third variable that is causing the change in the criterion variable. This is an example of a mediated relationship. So yes, there might be a causal relationship, but it's not the direct relationship that we're hypothesizing. It's being caused by changes through a third mediator variable. Another type of third variable that you might want to think about is a moderator variable. A moderator variable is a third variable that will influence the strength or the nature of your correlation. Now, it's not part of the causal chain. It's not that it is causing the change in the criterion variable directly, but it is influencing the relationship between your predictor and your criterion variable. So for example, maybe your ability to find joy and how that relates to life satisfaction will vary depending on whether or not you are a male or female, or whether you are young versus elderly, right? We might have these kinds of variables that influence how strongly the ability to find joy is related to your overall life satisfaction. So a moderator variable, if we're looking at joy and life satisfaction, maybe they're not taking into consideration that this relationship, even if it's causal, is going to be different for men versus women. All right, confounding variables. This is a third variable that is causing changes in both your predictor and your criterion variable. So it looks like there is a correlation. It maybe even looks like there's a causal relationship between your predictor and your criterion, but in fact, both of these are being driven by changes in a third variable, which is the confounding variable. So for example, we have hot weather. If it's hot, it causes an increase in increases in ice cream sales. Hot weather also tends to cause an increase in aggressive behavior. So it looks like increases in ice cream are correlated or perhaps causally related to increases in homicides, but in fact, both of these are being driven by this third variable. We could also look at our example of joy and life satisfaction, where maybe it's the strength of your social network. People who have a really strong social network are able to find more joy in their free time. They also tend to have higher life satisfaction. People who have a very weak social network maybe just don't find much joy in their free time, and weak social networks also mean you have lower life satisfaction. So it could be this third variable that is responsible for changes in both your criterion variable and your predictor variable, and it makes it look like these two variables are directly related when in fact they're being caused by a third variable. Okay, so these are all kinds of third variable problems that you guys need to be aware of, and why it's good to be skeptical of people trying to make causal conclusions from purely correlational studies. The last thing to think about is a spurious correlation, and this just means that there's random error or random variation that exists in the world, and sometimes we get things that are just randomly correlated, but that's just because of random variance. So it's a great website where somebody just takes variables that should have nothing to do with each other, like how much cheese is consumed and whether you die by becoming tangled in your bed sheets, and it shows how these things are correlated. And of course, the amount of cheese you eat is not going to cause or should even be related to death by tangling in your bed sheets. That makes absolutely no sense. But you can see that just because of random variance that exists in data and exists in the world, especially when we have large data sets, we tend to get these kinds of correlations. And so when you have correlations, especially if there's not any good theoretical or empirical research to back it up, be mindful that maybe this is just what we might think of as a type 2 error. It's just spurious, right? Okay, so I've talked about all of the reasons why it's making causal conclusions from correlation studies is limited and why you need to be cautious about this. So if we are limited in the kinds of conclusions we can draw from a correlation study, why do it at all? There are a number of reasons why doing correlational research is still really helpful. One, maybe you don't think that there is a causal relationship between these variables, but you think that they are related, and that's what you want to model. And that is totally fine. You are trying to model real-world relationships through a correlation, and that's perfectly acceptable. We don't think that these things are causally related, but we still want to see how they are related. Great. Maybe you think that there could be a causal relationship. However, for ethical or logistical reasons, you cannot do an experimental study. Right? If you're looking at how childhood abuse is related to adult depression, it would, of course, be highly unethical to randomly select some children and abuse them. So we can only rely on correlational research. It's used when we want to establish reliability and validity. We've talked about this for the past couple of weeks, and you might have noticed that the way we establish validity and the way we establish reliability is looking at correlations, right? If we want to look at retest reliability, we're assessing the extent to which the scores at time 1 are related or correlated with the scores at time 2. If there is good test-retest reliability, it means that people who score high at time 1 are also likely to score high at time 2. People who score low at time 1 are also likely to score low at time 2. That's a good correlation. That's a positive, strong correlation. If we are trying to establish validity, maybe we are looking at how scores on your new scale of aggression relate to a well-established scale of aggression. And we would hope that people who score high on your new scale of aggression are also going to score high on the gold standard scale of aggression. So we're using correlations to help us establish reliability and validity. We can also use correlations for studying historical events, again, things that we cannot manipulate. It's good for when we are interested in preserving the external validity. We don't want to control for a lot of things, which you would need in order to make causal conclusions. So if you really want to establish the extent to which your results generalize, maybe you want to look at correlational research instead of experimental research. It's good for preliminary research, especially when you're in a really, really new area and you're just trying to identify variables that might be interesting to follow up on in experimental studies. And finally, correlational research is really great for predicting behavior using linear regression. And that's what we're going to be talking about for the rest of today's lecture, is how we can predict behavior, how we can predict scores based on the correlation, based on the relationship that exists between predictor variables and our criterion variable. Okay. Outliers on a single variable or combination of variables can disproportionately influence the correlation, especially if the sample size is small. Now, while correlations can be indicative of causal relationships, we're unable to verify this because the situation has not been manipulated or controlled. Third variables may influence the strength and nature of the correlation. Moreover, changes in both variables may be related to a third variable and not dependent or related to each other. And finally, other problems with drawing causal conclusions include the directionality of causality, which cannot be determined, and the possibility that the relationship is spurious. Any questions before we continue? Everyone's good? All right, great. So then let's start on linear regression. So go back to your week club. I want to predict the overall life satisfaction. Now, I know that there's a correlation between these life satisfaction and joy. So what's the best strategy for getting the most accurate prediction? What do you guys think? Okay, so if we want to predict what somebody's life satisfaction score is, and we know that there is a relationship between life satisfaction and finding joy, the best way we can make this prediction is assume that people with lower levels of joy will have lower levels of life satisfaction, and people with higher levels of joy will have higher levels of life satisfaction. That is the most reasonable way of predicting your life satisfaction. We know that there is a correlation, a positive correlation that exists, so it wouldn't make sense just to pick a random number, right? That's perhaps not the best way of predicting what your life satisfaction score is. If we assume everyone has the same life satisfaction score as the population average, that could be a way if we know nothing else. Sure, that's not a bad way. But if we have more information about the relationship between life satisfaction and finding joy, then let's use that information to improve the accuracy of our prediction. And that's the basis for linear regression. So, correlations tell us about the relationship between variables. Right? It tells us not only are they related, but it tells us how they're related. Is it a positive relationship? Is it a negative relationship? And it tells us the strength of that relationship, or in other words, the reliability of that relationship. And that means we can predict with some accuracy what your score will be on a criterion variable based on how it is related to a predictor variable. If there is a positive correlation between height and weight, it makes sense that I would predict somebody who is shorter to have a lower weight compared to somebody who is taller, because these variables are positively correlated together. I wouldn't expect a tall and short person to have the same weight, right? I would expect there to be some differences or some variance in the weight based on whether they are tall or short, if a positive correlation exists between these two variables. So we can use the correlation between our predictor and our criterion variable to help us improve the accuracy of our prediction. Of course, the stronger the correlation is, the more accurately we can predict the outcome variable. So let's just say we are going to Universal Studios. And the entrance for a family of 4 is $250. And the rides are free, but you need to buy meals for everybody because you're going to be there for a full day. So let's just say it's $22 per person to get a meal. If we want to predict how much are you going to spend at Universal Studios that day, and all you do is you go in, you ride the rides, and you get 1 meal per person, we can predict this with pretty good accuracy. In fact, we can predict it with perfect accuracy because there's not any variance here. We know that the total is going to be $338 plus the sales tax, right? Because there is a relationship that exists between how much you pay per person for each meal and the entry cost. So that allows us to predict how much we're going to spend that day based on the number of people who we're bringing. And if we said, hey, Timmy, bring your friend along too, so now we've got 5 people, well, we can very accurately predict how much that's going to cost us with 5 people. We just do, 22 times 5, and we add an extra entry cost for whatever that entry cost is. So it's pretty easy to predict what the cost will be if there's no variance in the data and how these variables are related to each other. Now, normally there is some variance in our data that we're looking at. So if this is, and this is fully made up, but if we're looking at the amount of time you spend studying and your grade on the final exam. Well, we see that there are 3 people here who study 1 hour, and yet we see different grades on the final exam. And you can see that for lots of different values here, that the relationship between how much you study and your final exam varies. So we can't predict with perfect accuracy what your grade will be based on how long you study. However, so if that's all we know, and I asked you to predict your final exam score, or in this case, midterm exam score, it makes sense that you might say, well, what is the average? What's the average exam score? 56.3? Okay, that's what I'm going to predict that somebody else's exam score will be. That makes the most sense. But if we know that there is a relationship that exists between how much you study and your exam scores, and it looks like there is, we can improve our prediction accuracy. We wouldn't necessarily predict that somebody who studies only 1 hour is going to get a 56.3, and we wouldn't predict that somebody who studies 10 hours is going to get a 56.3. We might try to improve our prediction accuracy using the relationship that exists between the amount of time you spend studying and your exam score. So it looks like there is a positive correlation between these 2 variables, such that people who study less, while yes, there is some variance in the data, by and large, people who study less tend to have lower scores on their exam. People who study more tend to have higher scores on their exam. Right? So, if we look at the correlation output, if we did just a simple Pearson correlation, this can be verified. Yes, there is a correlation of 0.614 that is statistically significant, so that tells us that there is a pretty strong positive correlation between these 2 variables. Increases in one variable are related to increases in the other variable. So, if we want to predict what is the grade of somebody who studies 1.5 hours on their exam, well, if we're just using the mean of the exam scores, we would predict somebody gets a 56.3, which seems kind of high based on the relationship we know exists between studying and exam scores. That looks a little bit high, right? So it might make more sense to predict a lower grade for somebody who studies only 1.5 hours, maybe something like a 30. And if we're trying to predict the grade for somebody who studies 9 hours, we would predict something higher. We might predict something like an 80, for example. So we can improve the accuracy of our prediction of your exam score by using variables that we know are related to this variable. And that is the basis for linear regression. This line is called a regression line. This is the model. This is what we are using to predict our criterion variable or our outcome variable. So the regression line is the line of best fit. It's going to cut through the center of the data, and it's essentially the mathematical mean of the data. So linear regression allows us to predict the value of y, which is your criterion variable, based on how it is related to your predictive variable x. We're going to use this regression model, which has been fit using the ordinary least squares approach. This simply means that it goes through the center of the data. It is the best descriptor of your data. You could think of it as the average or the mean. Now, this regression model, this line, is defined by a certain model. It's called B1x plus B0 plus some error. This is how we would define your regression line or the linear regression. So this means that the value of y that we predict, y hat is with a little, like the little rooftop, that is a symbol for predicted value of y. So the predicted value of y equals B1x plus B0e. Now, what does this mean here? Okay, let's break this down. B1 is the slope of your regression line. It is the tilt of the regression line. Okay? What it's telling you is how your predictor is related to the outcome variable, your y variable. If you have a very big slant, that means that for every 1 unit increase in your predictor variable, you should see a very big change in your outcome variable. If it's pretty flat, it means that changes in your predictor variable are not going to result in a great change in the outcome variable. So B1 tells you the slope of the regression model, and B0 is your y-intercept. It's the starting point. It's what you predict the value of y will be when your predictor equals 0. So when our predictor is equal to 0, it's at the y-axis, hence it's called the y-intercept. It's where the line crosses the y-axis. This is what we predict the value of y to be. Think of like our example where the family goes to Universal Studios. If they don't buy any food, the starting cost is the entry ticket, that $235. That's the B0. That's the starting cost. And then for every meal you add, for every person who has a meal, you add $22 on top of that. So that's the slope. Okay? So the B0 is the starting point. It is what we predict the value of y to be when the predictor is set to 0. And B1 tells us how the predictor is related to the outcome variable. So for every 1 unit increase in our predictor, we see a very small change in the y variable, versus when the slope is very steep, for the same change in x, we now see a much bigger change in y. So this is telling us how they're related. And of course, it can be negative as well, right? So for every 1 unit increase in x, we might see a decrease in y. So it can be both positive and negative. It's simply telling us the relationship between our predictor and our outcome variable. Any questions so far? All right, so when we're thinking about the regression model, we're using this as a way of predicting an outcome variable, our y variable. And we're just going to predict it based on the relationship between our x and y variables. Easy so far. And we're going to make our prediction using the regression model, which is defined as the value of y when x equals 0. So when we study 0 hours, what is the average score on your exam? That's your B0. And then for every hour that you study, what is the change in the exam score that we would predict? So B0 grade when hour study is equal to 0. X is how many hours that you're studying, so we can change this. We might want to predict when X is equal to 1, what happens when X is equal to 1.5, what happens when X is equal to 9. That's what you're trying to predict, or that's the variable that you're changing. B1 is the relationship between X and Y, so that's the relationship between the number of hours you studied and your exam score. And then Y hat is the predicted grade that we're trying to estimate. Okay. Any questions so far? Okay, so B1 is the slope, it's the coefficient, and this tells you the change in Y for every 1 unit increase in X. Whether that change is an increase or decrease, it tells you how X and Y are related. Now, a lot of times we like to put this into standard deviations, because if I tell you that a change in a 1 unit increase in variable X is related to a 1.5 change in Y, you don't know how to interpret that. Is 1.5 big? Is it small? It's hard to know unless you're really familiar with these variables. You don't have a good sense for, is the change in Y of 1.5, is this a big change, is this a small change? So if we put it into standard deviations, it makes it easy because we all know what standard deviations means. So beta is B, the slope, but just in standard deviations. So that way we can say for every 1 unit increase in Y, this is the change in the outcome measured in standard deviations. So if I say, oh, there is a 1.2 increase in the Y variable, that tells you that's a pretty big change, right, when it comes to standard deviations. That's a huge change. If I tell you that there is a 0.5 standard deviation change in Y for every 1 unit increase in X, that gives you a sense for how much change we expect in our Y variable. So just by putting it into standard deviations, it allows us to have a better sense for the scale in which our predictor variable influences the outcome variable. Okay, now we can do the same thing with categorical variables. So what I was showing you earlier were 2 continuous variables. So that was the number of hours you studied and your exam score. But we can, of course, model the same thing with categorical variables. So if I'm looking at your exam score and I'm trying to predict your exam score based on whether you are a psychology major or not a psychology major. So I'm defining psychology major here as 1, not a psychology major here as a 0. Can I predict your exam score based on this variable? First, let's just check, are they related? Yeah, there seems to be a relationship, not as strong, but 0.228. This is significant. So we do have a reliable relationship between whether you are a psychology major or not and your exam score. So we can improve our prediction accuracy of your exam score instead of just using the average exam score and making that my prediction for everybody. No, I'm going to predict your exam score based on whether you are a psychology major or not a psychology major. That's going to help me improve my prediction accuracy. So here we can see that by and large, people who are psychology majors have higher exam scores compared to people who are not psychology majors. And so I would predict a slightly higher midterm exam score or final exam score if you are a psychology major versus if you're not a psychology major. Just like I would predict a higher exam score if you study more compared to if you study less. I'm simply using the relationship that exists between these 2 variables to help me improve my prediction accuracy. Okay? So this regression model, again, is defined by the same equation we used earlier. The predicted value of Y is equal to the starting value, B0, which is the grade, the average grade when X is equal to 0. Now, if I am defining being a psychology major as 1, not a psychology major as 0, that's how I've defined my variable. You recall, psychology major is a 1, not a psychology major is a 0. So, 0, the B0 is the grade when psychology major equals 0, which means that I'm looking at non-psychology majors. And then what is the increase in grade we expect when you are a psychology major? That's the B1. Okay, regression analysis allows you to predict the value of your dependent variable based on the relationship between that variable and a predictor variable. And this results in more accurate predictions of the outcome compared to if you were to just use the average of y alone. Now, the stronger the correlation is, the better your prediction will be. And the regression line represents the minimum squared error. It's basically the mean of your data. And it is a line of best fit. So we can use this to help us predict the outcome variable. And the regression line has a specific definition. This is the linear model, and it's defined as B1x plus B0, where B1 is the relationship between your x variable, your predictor, and the outcome. B0 is the starting value when x is equal to 0. That's always going to be the equation. Any questions? Yes? E is just error. It's just to remind you guys that this is always going to have some error in your prediction. So error is not something we can really quantify, but it's just to remind you that you can make a prediction, but it's going to be off a little bit always. Yeah, good. Other questions? Yes? Just write E. Yeah, it's just to symbolize that there is going to be some error that we cannot predict. Right, good. Any other questions? Okay, so we have created a model to help us predict the value of some dependent variable based on the relationship between that dependent variable and our predictor variable. So we're using the correlation to help us predict your behavior. Everyone's with me so far, yes? How good is our model? If we want to know how good is this regression model? Is it actually any good? Should we use it? I mean, I can make a regression model, but that doesn't mean it's any good. How do we know if it's any good, that we should actually be using it? We need to think about how well our regression model fits the data and how much error there is. If we have something like here on your left, this is what we might think of as being a pretty good fit. There's not a lot of unstandardized error. In other words, there's not a lot of non-systematic variance. We see that overall there is a pretty strong correlation between our predictor and our criterion variable. So the fact that we have a relatively strong correlation of 0.6 something, if I remember correctly, that tells us that this is a pretty reliable and strong relationship. So our regression model fits the data pretty well. There's not too much unsystematic error. Compared to here on your right, this is a pretty poor fit. There's a lot of unsystematic error. There's a lot of just random variance in the data. Our model is not giving us a really good description of what's happening, at least not one that's any better than the average of y alone. So if our model is a good model, we would expect that it is going to help us improve the accuracy of our prediction above what we would get from just using the average value of y. If there is a correlation of around 0 or close to 0 between x and y, what's the point of using that correlation to improve our prediction accuracy? There is none. We really only want to do this when the relationship between our predictor and our outcome variable is strong and significant, when it's reliable. And that's going to give us a more accurate prediction of the outcome compared to just using y, the average of y alone. Okay? So what this is pointing out to you is that the variance in the data is really important. How much variance do we have, and whether that variance is systematic or non-systematic. All right, so this is our example. We've got the average value of y is 56.3, and we've got our linear regression model, which is showing us the correlation between x and y. So this is, black line is what we predict, right, based on our relationship that exists between x and y. The red line is simply the average of y. This is what we predict if we know nothing else at all. If I know nothing else about you guys, if I know nothing else about how exam scores are related to anything else, then sure, I might predict that your average, that your score on the exam is a 56.3. But if I know that there is a relationship between studying and exam scores, then I'm going to improve my prediction accuracy using the correlation that exists between these two variables. So we can break down the error or the variance in the data by whether it is systematic variance or non-systematic variance. Now, remember that error is simply another word for variance. There is variance in the data, right? People who study for 1 hour don't always get the same grade. People who study for 10 hours don't always get the same grade. So there's some variability in the data. But some variability in the data is systematic. By and large, people who study less tend to get lower grades compared to people who study more. So there is some variance in the data that is systematic. People who study less have lower grades compared to people who study more. That is a systematic variance in the data. And this systematic variance we can call SS model, or sum of the squares model. This tells us the error in the data that our model accounts for. And this is the difference between what we predict using our regression model and what we would predict using the mean of y alone. We know that people, or at least we have a pretty good prediction, that people who study for 1 hour or 2 hours should score less than the average. People who study 10 hours should score higher than the average of y. So although the basic model, the mean of y, predicts everyone gets the same grade, we say, no. We're going to predict variance, right, in the grades based on how much time you spend studying. People who study more get higher grades compared to people who study less. And that is a variance that is systematic, that we can explain because we know that there's a positive correlation between these two variables. So this is the difference between what we predict using the correlation and what we predict using just the mean of y alone. It's the variance that makes sense to us. But there is some variance that doesn't make sense. There's just variance in the data that is due to noise, due to other stuff that we have not yet included in our model, variance due to just individual differences, right? Again, we have people who studied 1 hour or people who studied 2 hours don't get all the same grade. So we predict that people who study 2 hours will get a grade of 38. But that's not what everybody gets. So the difference between what we observe and what we predict is the non-systematic variance. This is the unexplained variance. We don't know why people who study 2 hours have different scores. We don't know why they didn't all get a 38. It's due to stuff that we just aren't accounting for in our model. So the SS residual is the sum of the squares residual. This is the variance in the data we don't explain with our model. And then the SS total is simply the sum of the residual variance and the model variance. So the variance that we can explain, the SS model, also sometimes referred to as the SS regression, this is variance in the data that we can explain using our regression model, using that correlation between x and y. It's the difference between what we predict using the regression model and what we would predict using the mean of y alone. SS residual is the variance we cannot explain. It's the variance that's due to other stuff that produces this non-systematic variance in the data. And again, we can do this with categorical variables as well. We have SS model, which is the variance we can explain, and SS residual, which is just the difference between every data point and what we would predict. Now, the standard error of the estimate is the average variance in the estimates that we have. You can think of this as Like when we have standard error of the mean, we also have standard errors of the estimate. So it's just variance in the predictions. R squared is the correlation between x and y squared. It's that R value, that Pearson's R squared. And this really means the proportion of the overall variance that we can explain. So if we think about that total variance in the scores, R scores tells us how much of that overall variance can we explain with our model. So R squared refers to the sums of squares model over the sums of squares total, which literally corresponds to the proportion of variance in the data that we can explain using our model. A good fit means that we have low sums of squares residual and high R squared. Whereas a poor fit means we have high sums of squares residual, lots of unexplained error, low R squared. So these will go together. Okay, now when we want to quantify whether the model is reliable, is it going to give us a reliably accurate prediction, at least more so than the basic model, that mean of y? We're going to calculate a ratio. And the ratio is the variance we can explain relative to the variance we cannot explain. Now, we're not going to use the sums of squares. We're going to use the mean of the sums of squares to make it more stable. So the mean squares is simply the sums of squares divided by the degrees of freedom. The same way you would calculate a normal mean, sum of the values divided by the number of values you have. It's the same idea here. The sum of the squared error divided by the degrees of freedom. And this gives you the mean square. So we're going to calculate a mean squared for the residual, a mean squared for the model. But this literally just comes down to the variance that we can explain relative to the variance we cannot explain. Okay, so we're just going to calculate a ratio, and that's your F ratio. So it's the mean squares model over the mean squares residual. And the mean squares are simply the average of your sums of squares, just to give us more stability. When we do this, this will give us an indication for the value of our model. Is it a reliable model? Is it giving us a more accurate prediction of y relative to using the basic model alone? All right, and the final thing that we're going to calculate is a t-test, which is a test of whether the slope of our model differs significantly from 0. If the slope of your model is pretty horizontal, right? If it doesn't really vary from being flat, that means changes in x are not related to any reliable change in y. So why would we use x in the first place? The t-test is going to tell us whether the slope differs significantly from 0, whether or not a change in x is related to a reliable change in y. Okay, so quick summary. Evaluate the fit and improvement of your model by assessing how much overall error is in the data, and if it can explain, that it can explain relative to the variance it cannot explain. Standard error of the estimate refers to the error in standard deviations. The effect size is simply the correlation squared. And assess whether changes in the predictor are related to reliable changes in the outcome variable using that t-test. Okay, I'm going to move on because we still have a lot to cover here. All right, so we've talked about how to do a linear regression with one predictor. Now let's talk about how to do this with multiple predictors. Now the good thing is it's exactly the same. There's really no difference. So we spent a lot of time going through how to do a linear regression with one predictor because the step going from one predictor to multiple predictors is really, really small. So it's pretty much the same thing that you've already done. Why are we going to use multiple predictors? Well, because having more predictors in our model can help us to account for some of that previously unexplained variance. If we want to predict your exam score, instead of just using hours studied, maybe we can also include how interested in the topic you were. How many classes did you attend, right? Other variables that we know are related to your exam score that could help us improve the prediction accuracy. So we're going to try to explain more variance by including more predictors in our model. Okay? Having more predictors that are reliably related to your outcome variable can help us improve the fit of your model. Now, do note that each predictor will have a different relationship with your outcome variable. Maybe we also want to look at how many, not only how many hours did you spend studying, how interested in the topic you were, and how many classes you attended. Maybe we also want to look at how much time did you spend, I don't know, playing video games. And we expect a negative relationship between how much time you spend playing video games and your exam score. So some of the predictors are going to be positively related. Some predictors might be negatively related. Some might be strongly related. Some might be more weakly related. Each predictor has a different relationship to your outcome variable. And we're going to need to take those things into account. Now, the good thing is the linear regression model is defined exactly the same. All you need to do is add a coefficient, add a term for every predictor you're adding to your model. So instead of just B1x plus B0, now we have B1x for our studying. Maybe we have B2, which is going to be for the number of classes you attended. B3 might be for how interested in the topic you were. B4 might be for how many times you played video games when you should have been studying, right? So it just means you add a term for every predictor you add to your model, but otherwise it's exactly the same. Each of those slopes, each of those B's, refers to the relationship between that predictor and the outcome variable. So it's exactly the same as what we just did. We have a linear regression model that we can predict the outcome, in this case the exam score, as a function of how that variable is related to a set of predictors. And we're going to try to predict with better accuracy your exam score using these predictors together relative to what we would predict using just the mean of y. Any questions so far? Okay, so let's say we want to predict your exam score. If, as a function of the number of hours you studied, as a function of whether you're a psychology major, and what year level are you? Are you a first year, second year, third year, or fourth year? We're going to use these three variables to help us predict your exam score. So our equation is equal to B0, which is the starting value of y, when all of these predictors are equal to 0. So it's just where it crosses that y-axis. That's the same. We have a term for every one of our predictors, which describes the relationship between each of these predictors and the outcome variable. Okay? So this is how we're going to define our linear regression model. This is how we're going to predict the value of y using the correlations. And again, this all comes back to the correlation. It's not difficult. We're just going to use a correlation between each of these variables and the outcome variable to help us improve our prediction accuracy. The only difference is that we're going to add more predictors to account for more unexplained variance. Okay, I'm going to let you guys read through the term summaries on your own just so we can get through more of the lecture. Okay, categorical predictors. Now, we do have we have one continuous predictor, number of hours you spent studying, two categorical predictors. Are you a psychology major? Yes or no? What year level are you? 1, 2, 3, or 4? So when we put this into our regression model, we need to code them a little bit differently. If we put psychology major, non-psychology major into any kind of stat software program, your stat software program is going to come back error, 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 because it doesn't understand what yes and no means. It doesn't understand what psychology major means, non-psychology major means. If I put 1, 2, 3, or 4 into SPSS, it's going to interpret that as a value, like a linear value. It's going to interpret 1, 2, 3, 4 not as a categorical number, but as a linear number. So it's going to interpret 4 as being twice of 2. That's not what we want. These are just categorical variables. So we need to change all of these categorical variables into a language that the statistical software can understand. And what does it understand? It understands zeros and ones. So we're going to tell our software program that psychology major is equal to 1, non-psychology major is equal to 0. Now again, guys, this is a categorical variable, so I could have flipped it around and said psychology major is equal to 0, non-psychology major is equal to 1. That's totally fine. Usually, you designate the level that is your control or your comparison level as 0 and the others as 1. So if I want to see what is the effect of being a psychology major on grades relative to non-psychology majors, I'm going to put non-psychology majors as my 0. But it's categorical. It doesn't really matter. So binary variables, super easy. 0, 1, nice and easy. Same thing goes, though, for your categorical variables with multiple levels. I just need to create multiple, what we call a dummy variable, where I have dummy variables for each one of my levels of my categorical variable. For each dummy variable, it's either a 0 for, it's either a 1 for that particular level or a 0 for all others. So you can see here that first year gets a 1 for a Y1, 0 for all others. Second year gets a 1 for Y2, 0 for all others, so forth and so forth. So when I put this into SPSS, very easy, you just ask it to create dummy variables for you. You don't even have to do it. It's going to create dummy variables where you can see year level 2 has a 1 under year level 2 dummy. Everybody else, all other grades, get a 0. Year level 4 has a 1 under the dummy variable for year level 4. All other levels have a 0. So it's just going to create dummy variables for us that puts these into zeros and ones so that SPSS understands what we're talking about. And it doesn't try to interpret this as a linear variable. Okay. So guys, let's go through how to do this in SPSS quickly. We'll go to regression and linear. Now put in the variables that are your predictors. So you've got grade as your criterion variable. That's what you're trying to predict. And the variables you're trying to use as predictors go into the box down there. Now, do note, you're going to choose one variable as your reference category. This does not get put into your predictor variables. So if I'm going to assess what is the effect of being a year 2 on your exam score relative to year 1s? Do I expect that the having a year 3 is going to increase exam scores relative to being a year 1? So I'm just going to choose year 1 as my comparison group. Now, that, again, that's fairly arbitrary. Maybe you want to choose year 4 as your comparison group. Choose one of these as your comparison group. Sometimes it makes sense. You know, no is usually the comparison group versus yes. But sometimes you just choose one. All right. So choose one of these levels, choose one of these groups to be the comparison group. And you're going to assess the effect of all of that category, right? So year 2, 3, 4, relative to your comparison group. So just choose one of these, and that does not go in here. All right, here's all the things you want to click. Some of these are going to be to check your assumptions. You can get a graph of the residuals. Again, this is just for assumption testing. I'm not going to go through it too much because we don't have a lot of time in lecture, but you can read about this in your textbook. But this is very similar to what you guys have already done in your 2131 when you went through assumption testing. Your book does talk about using the diagnostic criteria. I find that to be a bit advanced for this class. So I encourage you guys to read through it. I'm not going to expect you guys to be doing the diagnostic criteria, but it's good for you guys to read through and just have an idea for what he's talking about. Okay, so we have, starting off a correlation table, is just check which of your predictors are actually correlated to your outcome variable. And you can see that certainly psychology major and our study are significantly related to to your grade, what year level is not significantly related, so we're probably not going to get anything particularly helpful from this category, but we'll just see what happens. You will then see a box that tells you what you've put into your model. So just in case you forgot, or just in case you see it on an exam and you're not the person who put it into SPSS, this tells you what predictors are actually in the model. And then, before we get to the rest, let's just do a quick recap. Remember that when we do linear regression, we're trying to predict the outcome based on the relation between that variable and a set of predictors. That's the linear regression model. And we're going to judge how good is our regression model by looking at error. So we're going to assess the fit of our model by looking at how much error we can explain, how much variance we can explain. That's the sums of squares. Relative to the variance we cannot explain, which is the sums of squares residual. So sums of squares model is the variance we can explain based on the relationship that exists between our predictors and the outcome variable. Sums of squares residual is the variance we cannot explain due to all the other stuff that's affecting our data. Yes? Once we've calculated the sums of squares, we're going to just calculate an average variance explained, which is the mean squares model, and the average variance unexplained, which is the mean squares residual, which is simply the sums of squares divided by degrees of freedom. That's it. And then we're going to calculate a ratio of the variance we can explain relative to the variance we cannot explain. And this is going to tell us whether our model is a statistically significant, in other words, whether it is a reliable model, whether it is giving us a reliably accurate prediction of the outcome relative to just using the basic model alone. So the F is simply the ratio of variance we can explain to variance not explained. And this is going to tell us how good is our model. Do we have a significant model? Should we be using these predictors to help us predict the outcome? And then finally, we can calculate an R-squared, which is simply the proportion of the overall variance in the model that we can explain using our regression model. All right, this is all the stuff we just covered. How do we see this in SPSS? It's going to give us a model summary. So it tells us the correlation between our outcome variable, our Y variable, and our set of predictors. This is the multiple correlation coefficient. This is when you put all of your predictors together, they are related to Y at 0.636. So yeah, good. Our model seems to have a strong, all the predictors together have a strong positive correlation with our Y variable. So R is the multiple correlation coefficient, which includes all the predictors together. R squared is simply R that has been squared. It is the effect size, the overall proportion of that overall variance that we can explain using the model, using all of these variables together. So we can explain 40.5% of the overall variance. That's pretty good. Right? That's a lot of variance we can explain using this model. Now, do note that the adjusted R-squared is not something we would normally use. This indicates the generality of the model, and it provides a value that you might expect in the population. People don't normally report this. It might come in handy when you're trying to compare between models later on, like a 2-predictor model versus a 3-predictor model versus a 4-predictor model. But for our purposes here, you don't need to worry about this for now. Standard error of the estimate. This is the average variance in the estimate that we'd expect in the sampling distribution. So it's giving this to you as well. And then here's your ANOVA table. Now, this is always going to be in the same format. It's always going to show you the sums of squares for the regression model and the residual, which is the unexplained variance, and the total. It's going to give you the mean square. It's going to give you the degrees of freedom and the F. So this is exactly the information that you need to check, is your model good? And we can see that overall, there is a significant F, which means that the proportion of variance we can explain is reliable, that the variance we can explain relative to the variance we cannot explain is reliable. Any questions so far? Okay, so let's move on and talk about how we can assess each of these predictors, because so far, guys, the ANOVA put all of those predictors together. So the multiple correlation coefficient of 0.62 something is looking at all of those predictors together, but you guys saw from the correlation table that not all predictors are equal. Some of our predictors were in fact not even significantly related to our outcome variable. So what is the value of each predictor in our model? It's kind of like when you do a group project and you've got some people who are doing all the work and making the project good, and you've got maybe a couple people who are not contributing anything. Here, we've got an overall pretty good group project, but not all of our predictors are contributing equally to how good that model is. So how can we suss that out? We're going to start using the t-test. Remember that the t-test tests whether the slope of your predictor differs significantly from zero, whether it is different from horizontal. If the slope does not differ from zero, that means the change in that predictor is not reliably related to a change in the outcome variable. So, digit, right? It's not helpful. It's not helping you out at all. If the slope does differ significantly from zero, it is helping. A change in that predictor does relate to a reliable change in the outcome variable. So that's going to help you improve the prediction accuracy. So what we're going to do is conduct a t-test for every one of our predictors to assess which predictors are useful, which predictors are just hanging out and not really contributing. Now, you don't actually have to do this. Thankfully, SPSS does it for you. So we have a coefficients table, which is going to tell you how each of the predictors is related to the outcome variable. So, first of all, we can see a column for the t-test. This is the t-test that assesses the slope for each one of our predictors, and it's going to tell us whether that slope is significantly different from zero. So that's quite helpful. So we see a t-test for every one of the predictors right there. And then we can look at the slope for each one of our predictors. Now, intercept, the top line for constant is your y-intercept. So this tells you the starting value of y when all of your predictors are set to 0. So this is that B0. And then these are the B's for every one of your predictors. So this tells you how each of your predictors are related to the outcome variable. For every 1 unit increase in our study, we expect that the grade is going to increase by 4.434 points. All other variables remaining the same. This is while holding all other variables constant. So we would expect there to be a change, an increase in the exam score for every 1 hour more that you study. Now, when we do categorical variables, we are going to compare the effect of each level of our categorical variable to that control level we did not include, the level that was coded as 0. So what we're saying here is that relative to non-psychology majors who got coded as a 0, being a psychology major is expected to increase your exam score by 5.363 points. All other variables remaining the same. Relative to first-year students who got coded as 0, those were my control level. Being a second-year student is going to increase your exam score by 2.830 points. Relative to first-year students, my control group, being a third-year student, will increase the exam score by 0.821. And again, relative to first-year students, my control group, being a fourth-year student, will decrease my exam score by 0.536 points. Decrease because this slope is negative. Now, of course, year 1 or year 2, year 3, year 4, those slopes are not significantly different from 0. So we don't actually think that there's going to be a reliable change in the exam score based on what year level you are, because the slopes don't differ from 0. Those significance values are not less than 0.05. But, and it is marginal for the psychology major there. So we don't expect there to be a reliable change, but if there was, this tells you how we expect the change to look. Now remember that sometimes we like to put these slopes into standard deviations because, we have got categorical variables, we've got continuous variables. Maybe sometimes we're looking at hours studied, maybe we're looking at the number of classes you attended, right? So these are all very different scales, and it's really hard to know how to interpret what a 5-point increase means relative to the other variables. So we can put them in standard deviations, and this is how we can interpret which variable has the biggest effect on the outcome variable. So when you put it into standard deviations, this is telling us that the hour studied has the largest effect because a change in hour study results in a 0.591 standard deviation increase in the exam score. All right, other things to look at here, we've got, these are values to help you assess multicollinearity, which means that you've got a really strong overlap between your predictors. Sometimes we use predictors that are basically telling us the same thing. If I was looking at the number of classes you attended, and I also included into my model the number of classes you skipped, it's kind of redundant, right? One is telling me the same information as the other, which is going to result in some instability in my model. And I don't want to have variables that overlap too much in terms of the variance they can explain. That doesn't make sense. So we can use multicollinearity statistics to help us weed out and to detect any kind of multicollinearity. And if you do have problems with multicollinearity, you maybe want to get rid of one of those variables. So you can use these as a ways of detecting variables that have too much overlap in the variance that they can explain. And then you also get columns that relate to the correlations. These are the correlations between each of your predictors and the outcome variable while holding the others constant. Now, the zero order correlation actually doesn't hold anything constant. So when you do a standard Pearson correlation, this is what you're going to get as the zero order correlation. This is not holding the others constant. Partial correlation is the correlation between that predictor and the outcome variable while holding the other variables constant. So this is the unique correlation between that predictor and that outcome variable. And your part correlation is the correlation you get between that predictor and the outcome variable while holding constant the variance in the predictor but not the outcome variable. It's a bit weird, but if you think of partial as being you're holding constant the variance between between x and y, you're holding constant all other variables. Part correlation means you only remove the variance due to other variables in the predictor, but not in the outcome variable. It's just another way of assessing the relationship between x and y. So sometimes you can do this while holding constant all other variables in both the predictor and the outcome variable. Sometimes you might want to remove the variance only in the predictor, but not the outcome variable. So this is all the information that you're going to get from us, SPSS. So the coefficients table is useful. Do use theory to guide which coefficients or which predictors to add to your model. The more predictors you add to your model, the more power you lose. So it's good to add predictors to help you explain more of the variance. Right? We want to try to explain as much of the variance in the data as possible so we can have the best and most accurate prediction. But we don't want to add variables that are not related to our outcome variable. That doesn't make sense. They're not helping us in our prediction. So before you start adding variables to your model, of course, use prior research to help inform you which variables are going to be best, which variables are most likely to be most informative in your model. Do go beyond standardized regressions to determine relative importance. So just look at overall data. Don't use one value. Look at all the values you have. And avoid dichotomizing any continuous variable. So if we're using our study, that's a continuous variable. Try to avoid saying studied a lot, studied little. Right? That tends to remove the sensitivity of your predictor. So try to, if it's a continuous variable to start with, leave it as a continuous variable. Don't dichotomize your continuous variables. All right, final things to talk about, guys. So do check that you have a continuous outcome variable. So linear regression is when you are using a continuous y variable. You can have continuous or categorical predictor variables, but the outcome variable needs to be continuous. If you have categorical variables, make sure that you dummy code them into zeros and ones. And if you have more than 2 levels, you will need to have multiple dummy codes. Check that there are significant zero-order correlations between your predictor and the outcome variable. If there's not a significant zero-order correlation, it may not be one that's worth including. So do just check for those things. There should be linearity between the predictors and the outcome variable. Of course, that only refers to continuous predictors, but this is a linear regression analysis, so each continuous predictor should be linearly related to the outcome variable. You should have independence of errors, normal distribution of errors, and homoscedasticity. So these are all of those checks for bias and assumption testing that you guys would have learned in 2131. Just make sure to review your notes because the same things you need to check here. Now, if you have outliers, do make sure that you're checking for any kind of outliers because, again, the basis of linear regression is a correlation. And you guys have just learned that outliers or extreme data points can have a disproportionate influence on correlations. So check for any extreme outliers in your data and check for multicollinearity, which we've just discussed was that tolerance and variance inflation factor. So again, multicollinearity means there's a strong correlation between your predictors. They overlap to a great extent on the variance they can explain, which can produce instability. You don't want that. You don't want to have number of classes you attended, number of classes you skipped, and your model. They tell you the same thing. So choose one. So follow the same rules in terms of assumption testing that you have learned in 2131. Do check your textbook for more information about these things. And again, regression diagnostics, super helpful, but not something I expect you guys to know at this level of your career. There is a really nice flowchart in your textbook that helps walk you through the steps. I think these are really great. So if you get confused, refer to your flowchart here. And that's it. If you have questions, again, check your textbook. I try to stay close to it so that you have this as a resource to go back to all the time if there are things you missed in lecture. You can always write questions on the discussion forum or email me for help. So we have 5 minutes left, which is all I need. So let's go to Woo Clap, and then you can do the final. Okay. Correct answer is B. So what does it mean if the slope of a regression line is negative and steep? It means that increases in the predictor correspond to large decreases in the y variable, right? If it's negative, then it means that every 1 unit increase in x is correlated with a decrease in y. And if it's steep, it means that there is a large change in y for every 1 unit increase in x. Great. Next question. Okay, so what is the null hypothesis for the ANOVA? Okay, so correct answer is A. The variance explained will not be significantly different from the variance unexplained. Remember that the ANOVA, that F ratio, is the mean squares regression over the mean squares residual. So it's the variance we can explain relative to the variance we cannot explain. So the null hypothesis is that there is no difference between the variance we can explain and the variance we cannot explain. All right, Good. Yeah, and any difference we observe is actually just due to sampling error. So that's your null hypothesis. Good. Next question. So in a regression line, the blank, the standard error of the estimate is, the more accurate the predictions are. Okay, correct. Yes, smaller. So the smaller the error of your estimate is, the more accurate it is. It means that you are doing a pretty good job of predicting the outcome. It means there's not very much difference from one prediction to the next within the sampling distribution. Good. Okay, what would happen to the coefficient B if R is negative? Okay, correct answer. It will also be negative. Remember that the coefficient relates to the relationship between your predictor and the outcome variable. So if the coefficient is negative, that means that the correlation between these variables is negative as well. That's what it's representing. So the coefficient is representing literally the correlation or that relationship between your predictor and the outcome variable. Good. What is the effect of making sum of squares residual larger? All other things remaining the same. Correct answer. The standard error of the estimate will also be larger. Yes. So if you make the non-systematic error bigger, that's also going to result in more variance in the prediction accuracy. Good. All right. Last question here. Which variable has the largest relative influence on the outcome? All right, correct answer is D. Variable D that has a beta minus 0.36. Remember that beta is the slope, it's that B coefficient that has been put into standard deviations. So this allows you to compare between your predictors because it's all on the same scale now. Great. Okay, guys, any final questions before we finish? Please make sure to review your textbook because the linear regression model we've discussed today is the basis for the following lectures. So do make sure that you review your notes. Any questions you have, you can always put it under the discussion forum as well. Thank you very much. See you guys next week.